Alright, hello again. Here we are for part 2 of today's lecture, the 16th lecture in our video series. Today we're talking about, in this portion of the lecture, we're talking about, moving on to a new topic, impulse and momentum for rigid bodies, and angular impulse and momentum in particular. So you've already looked at impulse and momentum before, but now I'd like to look at angular impulse and momentum, both linear and angular. I'd like to look at impulse and momentum for rigid bodies, both linear and angular. So let us consider this. So we finished our brief introduction to energy methods, and now we want to look at the third tool, which is impulse and momentum methods. So as a reminder, in this course we have three big tools. We have three big families of tools here. So we have three main families of tools, as we've discussed, and each of these have certain things that they're very good for. We have tools of, obviously, forces and accelerations. We have we basically have tools of Newton's second law, which is basically our F equals ma type problems. Sum of forces equals mass times acceleration. We have energy method problems, which we have just finished working with for now. We have energy method problems. And we have impulse and momentum problems. And each of these are sort of well situated for certain types of systems, or certain types of inputs, or certain quantities that we're considering. This is very good for forces and accelerations. Forces and accelerations. This is very good for velocities and displacements. And this one is very good for velocities and time. Velocities and time. That's what this one really, that's what this method really excels at. So we've looked at this one, we've looked at this one, and now we're going to look at this one. All right. And for this, our guiding equations are going to be as follows. Guiding equations. And we have seen this already for systems of particles, but now we'll be seeing it for rigid bodies. Might have something for the linear case, just like in the previous system where we looked at both linear and rotational, or translational and rotational kinetic energy. We'll do the same thing for impulse. So we have mv1 plus the integral from t1 to t2 of f dt. So mv1 plus the integral from t1 to t2 of f dt is equal to mv2. Is equal to mv2. And then ig, or the moment of inertia about the center of gravity, times omega 1 plus the integral from t1 to t2 of the moment, mg dt is going to be equal to ig omega 2. Ig omega 2. So the integral of the moment with respect to time added to the original rotational momentum will give us the final rotational momentum. So again, this is a matter of momentum. This is linear momentum. So let me annotate this. This is linear momentum and angular momentum. And angular momentum. Linear momentum and angular momentum. All right. And let me give you a few more notes on this. So a few other items. Other notes. It's going to be very well suited to problems with velocities and time in them. with velocities in time. And this is actually really our only system, or the only practical method, only practical way to deal with problems involving impulsive motion and impact. Problems of impact and motion, and impulsive motion. Problems of impact and impulsive motion. Impact and impulsive motion here. All right, so let's move on here. Okay. Let's see here. Now, we could look at this from the point of view of systems of particles again, but let's look at this conceptually for a rigid body. Why does this work? Well, rigid body, impulse, and momentum. Rigid body, impulse, and momentum. Well, let us consider plane motion. As in most things in this course, we work primarily with plane motion. Let's see here. Consider plane motion. Plane motion of a rigid body. Well, I'm going to look at three cases, or three steps here. This plus this yields this. And then I'll try to draw the same potato rigid body for each of these three cases. Kind of looks like a kidney bean or something. Anyway, so let me say that this is the same object. So pretend the drawings look alike, and they use the same object. And there is a center of gravity, the same center of gravity for each of them. Same center of gravity here. And we know that we can always reduce the state of, it is possible, as we have seen previously, to reduce the behavior of a planar object into two things, really. We can say that this thing has a certain rotation about this axis, and it has a certain translational velocity. So I could say that this thing has a certain rotation, a certain linear velocity, v1, and I'll say v1 bar because we're talking about the average linear velocity, and also it has a certain omega 1. However, if I want to look at this in terms of point of view of momentum, I could say that not only does it have a velocity v1, but it has a linear momentum v1, so that would be not just v1, but mv1. And same thing here, instead of having just being omega 1, this would be I bar omega 1. So, in other words, initially, I can completely describe at a given instant, I can completely describe the motion of this object using two criteria. I can describe its motion in terms of the average translational velocity of the, or the translational velocity of its center of mass, and also the rotational velocity about that center of mass. Or, if I want to look at momentum, I can say that this has a linear momentum, that is the mass of the object times the linear velocity of its center of mass, and then it has a rotational momentum, that is its angular velocity times its moment of inertia. Then I could apply a series of forces to it. I could apply a series of forces over a length of time. Basically, I would apply F dt. And these forces then would collapse to both I could average these forces into a force and a moment, and these would then produce some final value that is I bar omega 2 and mv2. mv2. Maybe v bar 2. And these forces, I could also collapse them if this is like F1, F2, F3. I could also say that this is equivalent to, I could also say that this system is equivalent to some force pushing applied to the center, F equivalent, and then some moment. I could turn all of these forces into one equivalent force, the equivalent linear force, and then also the whatever tendency I could add their tendencies to cause rotation about the center of mass by taking the cross products and the cross products of the vector to the line of action of each force and the vector of each force, and I could find the moment therein. So again, we know this from statics, we can always reduce a system of forces into a moment and a force. And so we can see here that we'll have three equations of motion. From this, we will gain three equations of motion. Three equations of motion. One, summing, let's say summing momenta and impulses, momenta being the plural of momentum, and impulses about x. Two, summing momenta and impulses about y. And three, summing and equating let's say moments and angular momentum. And we'll look at some cases of that. And considering angular momentum. Okay? So next I want to look at the concept of impulse momentum diagrams. Fun. Impulse momentum diagrams. Okay? So I'm going to work through the concept of impulse momentum diagrams by working through a simple example. So here, impulse momentum diagrams. Okay, so I'm going to write this out first, write my prompt out first, and then I'm going to work through the diagrams. So, a sphere S hits a stationary bar, AB, and sticks to it. And we'll draw this in a second. And sticks to it. Draw the impulse momentum diagrams. The impulse momentum diagrams for the bar and ball separately. ball and bar separately. Time 1, we always need to have time 1 and time 2. Time 1, immediately before impact. And time 2 immediately after. Immediately after. Immediately after. Let's see here. Okay. Let's see here. Now, immediately after, I'm going to have this system here, and so let me draw the system below. This is not the impulse momentum diagram yet, but this is the system as was given to me. So I'm going to have a pivot at point A, just going to be a simple vertical bar. It's going to hang down like this. And let's see here. I'm going to have some sphere S flying along here, and it's going to be a sticky sphere made of sticky glue or something. So this will be VS here, and this is again our sphere S. It's going to stick to the somewhere at the end of the sphere here. Well, I'll say I will actually model it as sticking exactly to the end of the sphere, which wouldn't be totally possible, but that's okay. Then I will say that this, let me label some points here. This is point A and point B. B is at the end of the rod. And so I will say this thing is going to stick right at point B. And then, of course, I will need my center of gravity G. And I'm going to say this is just halfway down the middle because I was not told one way or another. And if we're not told, then it's a reasonable assumption that that the center of mass is halfway down the rod. And then we are given the dimensions. Actually, we were given the location of this, sorry, but that assumption was correct. Dimensions here, also given, but this is 0.6 meters and 0.6 meters. And 0.6 meters. And 0.6 meters. All right. And I want to, so this is the system that is given, and I want to draw out impulse and momentum diagrams for each of our systems here, or for each of our objects here. Okay? All right, so first let us look at the ball. Consider the ball. Impulse momentum diagrams. Let us consider the ball. And we'll look at this here. So all of this is going to be based off of this idea here. We have this, whenever I draw an impulse momentum diagram, it's going to be based on, I'm going to have an initial state, a change, basically the initial state of momentum, both linear and angular if applicable. The final state, the final state over here, both the linear and rotational as appropriate. And then I'm going to have the impulse states. This is initial momentum, final momentum, and then impulse. So we'll have an initial impulse diagram, we'll have an initial momentum diagram, a final momentum diagram, and then an impulse diagram. And that's the basic method for setting these things up. So I'm going to have the ball here, and I'm just going to draw the ball 3 times. And initially this is going to have, and I could label this however I want, but on each of these I'm going to show either the impulse or momentum on the system or on the object. So I said that this thing originally had speed ms, so I'm going to say, I'm not going to label its velocity, but I'm going to label its linear momentum, which is ms vs. MSVS. Then its final momentum will be MSVS prime. MSVS prime. It's just going to, it doesn't initially have any rotation. We're just kind of, we were not given that it had any rotation. We're not given any we're not given any information about it having any kind of rotation. So if we weren't told that it had some sort of rotational velocity, even though it probably did in real life, we're going to assume that it's 0. And so it's going to have some sort of, at the end, it's just going to now eventually I could consider it having some sort of rotation as a joined object with the rod, but for now I'll just say immediately after impact it just has some other linear velocity. But really about its own mass center, it's not going to have any kind of rotation because it's rigidly now connected to the rod. And what's going to change this? Well, what's going to change this is the impact, or the impulse of the impact. So I'm going to say F impulse times delta t. And I'm drawing it this way because there must be a force to the left applied to the ball in some manner, because initially it is, it's definitely going to be giving some momentum to the rod. So if this thing was actually if the ball was experiencing an impulse to the right, well then that would be violating conservation of momentum. And let me label this. Let me label these again. Let me label this. Give us a little more annotation. This is momentum of ball before impact. This is the impulse on ball and this is the momentum of ball after impact. Momentum of ball after impact. And this is not a quantitative example, so we're not actually going to calculate Vs prime, but we could use these to calculate it if we did have some sort of numerical problem. And this is the momentum of ball after impact. After impact. After impact. Then I could set up something similar for the bar. And through this, we'll actually get some clues on how to handle impulse and momentum type problems, or systems of objects anyway. So I'm going to have the G here. G, A, and B. And again, I am not drawing forces on here. I am drawing momentum. So I'm going to say that this is, I will use perhaps, what can I use? I might use, let's use R for this, although I could really use whatever I want, maybe R for rod. So I have an MR-VR, and this is going to be equal to 0 because this is the initial momentum of the ball, or sorry, of the bar or rod. Then I'll have a rotational, and this is I bar omega is equal to 0. I bar R omega R, and this is equal to 0. So this here, again, this here is this, let me label it maybe up here. This is rod momentum prior to impact. And I could also show a plus here and an equals. And then I want to show the rod with its impulse, or F impact. this here, and I have this again. Now, it is important to take note of this, that whenever I draw a impulse diagram, it is very important to draw all of the forces that are on this object. It is important to draw all of the forces that are on this object. And in this case, I actually have multiple forces that are on this. Here, the only force that was acting on the ball was the impact force. It was flying through the air. So the only force that could act upon it was the contact force between the ball and the end of the rod. Now, the very first thing I'm going to draw is that impulse force, and I'm going to say it's equal and opposite. Whenever two objects collide, I do know that they're going to exert equal and opposite forces on each other, and so this is going to be F impulse, or F impact, I should say, times delta t. It's going to be the same force basically whatever force is applied to the ball, an equal and opposite force will be applied to the end of the rod. Now, it doesn't matter which way I set these up, at least in the sense that I can make this one go to the right and this one go to the left, but it is very important that when you're setting up these diagrams for systems of objects, or for systems of objects or for systems of rigid bodies, that you use compatible forces. You must set up your diagrams with compatible forces. Just put that in your notes. It is very important to set up diagrams with compatible forces. If you don't, you're going to get something wrong. In the sense that, if you look here, I don't care which way these go. I mean, you can set up your equations with these going either direction. You can set this one up now, this is something that we can probably just look at and figure out which way it's going to go, but if you had a more complicated system, it may not be so intuitive, or you may not be able to figure it out using such intuitive methods. And so instead, you would have to, you might just have to guess one way or another. But it doesn't matter. As long as I'm assuming compatible forces and compatible impulses, it doesn't matter. If I get a negative number, no big deal. I just know that they're in reality going the opposite direction. But if I set this one to the left and this one to the left, suddenly I'm in trouble. If I set both of them to the left, I'm assuming from the get-go something impossible. I'm assuming that both forces act to the left, which is impossible. That would be a direct violation of Newton's laws. You know, we know that for every action there is an equal opposite reaction. If I'm applying if I apply a force if I lean against the wall with a force of 10 pounds, then the wall is going to lean back on me with a force of 10 pounds. All forces in the universe always must exist in equal and opposite pairs. And if you assume that they don't, well, of course and then you try to apply the laws of physics to them, you're going to get the wrong answer. Which will either, if you're on an exam, it's going to lose you some points on an exam, or if you're a practicing engineer, you might kill someone. So anyway. But that's what happens when you try to violate the laws of physics. Physics pushes back. So there's our G. Let me put a plus sign here, equal sign here, and I need to add two other things: the AX, the support forces, AX and AY, and I'll go ahead and just use the same delta T. And then at the end of this is going to equal here, and these are just the support forces. The thing still is going to be supported somehow, so we need to consider that. And this is then going to equal our final condition.
We'll take into account the force of G.
The force of G, I couldn't. Okay, so the question is, what about G? What about gravity? And actually, that is a very good question. Why would you're talking about the force of gravity, the weight of the rod? In this case, that's actually not important, because remember, I'm looking at this immediately before and immediately after. But that is a very good question. And if I was looking at anything except that particular location, if this thing was at an angle, then I would actually have to include the gravity, because that gravity would generate a tendency to rotate. However, though, it would generate a tendency to cause the center of mass to translate and rotate. But because this thing, at this particular instant, it's hanging vertical, which means if this ball doesn't hit it, that rod will happily just hang there until the end of time without any change in position whatsoever, because the vector of gravity is passing right through its center of mass. It's already in its lowest position. Gravity wants things to be as low as possible. If it's already as low as it can get, it's not going to cause any further tendency to translation or rotation. But So as long as it's hanging vertically, we're fine. But if we have this thing at any other location, then you'd want to do something. So if I was trying to set up a more general dynamics problem, like say I wanted to model this thing's motion versus time, what I would want to do is I would want to set up that gravity vector as a function of theta, and then do an analysis, maybe an integration versus theta, or something like that. But that would be a wee bit more complicated. And then at the end of this, after all of this impulse, we'll have a final momentum that is mb vb prime, mr vr prime, if I'm going to be consistent, mr vr prime, and then we'd also have some sort of rotation, some sort of rotational momentum, which I would call ir omega r prime. Omega r prime. And also, let me label these again. Let me provide some final labels to this. And I do have one final note. Not final for the day, just final for this problem. Not so lucky yet. This is the impulse on rod. And this is the momentum on rod, or of rod, after impact. And we're talking about immediately after impact. After impact. After impact. Let's see, one other thing. Now, it might be tempting in this case, because you notice in this case, for this object here, we didn't have any kind of rotation, right? So it's tempting to say, well, if this one only has linear momentum, maybe this one only has rotational momentum, right? It's tempting to say that. But in this case, at this instant, that might not actually be true. It's going to have, and any idea why that is? Why can I not say that this has, even though this is not free to move in space, like it is stuck rotating about the support here. So why can't I just say, oh, it only has rotational momentum? Any idea? It might be tempting to say it has no linear momentum, it has only rotational momentum. Just like the ball here, we were able to say, oh, it doesn't have any rotational momentum, it's not spinning, it only has linear momentum. So it would be very, at least to me, it'd be very tempting to say, oh, this thing's rotating about a fixed point, it only has rotational momentum. Why can't I do that? Any idea? Well, it could break, but more importantly, it's not rotating about its center of gravity. It's not rotating about its center of mass. See, the center of mass is here, the support point is here. It's rotating somewhere other than its center of gravity. Now, if this were just like a bar that was just supported here, and the thing and the ball came up, stuck to it, and then just spun around like a wheel like that, then that would be fine. In that case, we could actually say that the thing had no translational momentum, because on average, the center of mass would not be moving at all. The center of mass, again, would not be moving at all. But in this case, it's the pivot point is not connected to the center of mass, or is not positioned at the center of mass.
So the center of mass is translating.
Yes, exactly. At this instant, the center of mass is translating. That is why we have linear momentum immediately after impact. All right, moving on. Okay. So let's look at another case of this. Here. Let's consider more of the principle of impulse and momentum. Some more on the principle of impulse and momentum. Not to be confused with principle PAL, which would be a very strange school indeed. I made a spelling joke. Ugh. So sorry. No, I'm not. Anyway. Okay. So let us consider, in particular, I want to look at fixed axis rotation. So I want to consider a general case of the bar that we just saw. So let's look at fixed axis rotation. fixed axis rotation. And so let us consider a potato, or as we sometimes call it, a general two-dimensional rigid body is probably the technical term for it, or you can just call it a potato, whatever we prefer. Although I suggest on the FE exam you refer to it as a general rigid body, not a potato. Anyway, well, I don't think you have to write anything like that out on the FE exam, but if you ever are asked to prove something in an academic sense, I suggest using the term general rigid body rather than a potato, but for our class we can use the term potato. So anyway, let us say we have this here. Let's look at this. Here. Again, fixed axis rotation. So we're going to have 2 points. One, the center of mass G, and then the allowed point of rotation, O. The allowed point of rotation, O. And let's say I had this here. We had some angular rate of rotation. This here. Let's say we have an omega here. This thing is rotating about here. Omega. And according to the principles we've already seen before, this rotation could be translated into 2 things. We could say that even though this thing is rotating about O, we could consider it 2 different kinds of motion. One, a linear momentum about the center of gravity, just like with the rod we saw earlier, m v bar and I omega. So it would be the same omega for both cases, but we're just adjusting it by adding this mv up here. I omega. So these 2 systems are effectively equivalent, and let us say that they're separated by a certain distance. Oh, let's just call this r. A certain distance r for radius. A certain distance, oh, maybe even r bar. R bar. Okay, for fixed axis rotation, let us consider the angular momentum about O. The angular momentum about O, the point of rotation O, well, I again am saying that this is equivalent here. I omega, the moment of inertia of the whole thing calculated about point O, let me clear that's point O here, times omega, and again it's the same omega for both of them, plus, or is equal to, I bar times omega, plus, now it has this linear momentum, but since I'm looking at this from the point of view of angular momentum, I need to transform this linear momentum into an angular momentum, and that would just be mv bar times r. So I can transform a linear momentum to an angular momentum by multiplying by the moment arm, which in this case would be r bar. Then I could say that I could transform this. I'll keep this as, and this is I bar. I could translate or transform this. I could transform the V bar into R omega, because I know V bar equals R omega. So I could say this is then M R bar times omega times R. Or I could say this is I bar plus m r bar squared times omega. This is getting very, this is starting to remind me a lot of the parallel axis theorem. But anyway, then if I equate the moments of the momenta and impulses about O, so set up my momentum impulse equation, the moments about O, and the moments, let's say, the moments of the momenta about O, momenta and impulses about O. And impulses about O, I could have the following. Well, I would say that IO omega 1 plus the summation of any moments about O dt, or actually the sum of the integrals, sum of the integral from t1 to t2 of mo dt is equal to IO omega 2. And so from this, because we're doing moments about O, the pin force, any kind of pin force at O, will not contribute anything to the moment at O, because those have no moment arm, obviously, about O. Okay? So let's look onward. Let's continue onward. And I want to just give a few more notes, and then I believe we can look at some examples here. So let me see here. Let me take a look here. I think we're good. Or we have a few more things about momenta, and then we'll look at some. I just have a few more notes to go over, and then we'll look at some examples, some example problems. So let us look. I want to give you a few notes on systems of rigid bodies. Systems of rigid bodies. So again, the motion of several objects. Several objects can be analyzed. By applying impulse momentum principles to each of them separately. By applying impulse momentum to each separately. Both linear and rotational. To each separately. Next. For problems with only 3 unknowns, 3 unknowns, well, we saw earlier when we were looking at systems of particles or systems of bodies that we can ultimately solve for 3 unknowns for any given body. So if you have a problem with only 3 unknowns, it may be convenient to just sum about the whole system. Be convenient to sum impulse and momentum about the whole system. About the whole system. Next, each diagram or for each moving part, an initial momentum, final momentum, and impulse diagram is needed. But also, diagrams should include momentum and vector and or couple for the middle diagram. A momentum vector and or a momentum couple. Momentum couple would be for our angular momentum, and a momentum vector would be for our obviously linear momentum. So I should say this would be not in the second diagram, but the first and the third diagram. Diagrams should include a momentum vector and momentum couple if applicable. And then if there are any internal forces need not be considered, as they will not result in any net change in momentum, because they're equal and opposite. So you don't really need to consider forces that are internal to the system in any net change in the momentum. So you don't necessarily need to consider them. But you can if you want. If you do it right, it's not going to affect things. All right. Okay. Next, the final concept before I look at some example problems will be the conservation of angular momentum. And this is something you've probably seen before, so hopefully it's fairly quick to get through. And that will be the conservation of angular momentum. Let us look at the conservation of angular momentum. Conservation of angular momentum. Now, this all comes down to one thing, and that is, if I look at my balance of angular momentum and moments equation, if I have IG omega 1 plus the summation of the integral from t1 to t2 of mg dt, this will be equal to IG omega 2. However, this mg dt is something that must be applied from the outside, the external part of the system. This must come from outside the object. A body cannot generate a moment about itself. You can, without some sort of mass interaction or force interaction with an outside object, you cannot generate a torque about yourself. So your angular momentum is conserved. So in effect, if we're looking at a single object, this is going to be 0. This is going to be 0. Anyway, this is going to be 0. However, and the classic example of this is a skater. You've probably seen this the classic graphic before, where you have a skater. So for example, a skater, so this would come down to IG omega 1 equals IG omega 2. So if you have a skater that, you've probably seen a figure skater before in the Olympics or some other case where the skater starts with their arms outstretched and then they pull their arms in, and so they're initially spinning quite slowly, but then they pull their arms in, their rate of rotation rapidly increases. And this is because they start with a fairly large moment of inertia with their limbs far outstretched, and when they pull them in, their moment of inertia gradually decreases, or rapidly decreases, I should say. And because their moment of inertia is going to decrease, the only way their angular momentum can be conserved is if their angular momentum can be conserved is if their angular velocity, the revolutions per second, dramatically increases. And so that's one case of this, that everyone's seen that before. But what I think is something even cooler is, of course, out in space, like all cool things. Anyway, and I want to consider the example of pulsars. Pulsars.
Yeah, that.
Y'all know what a pulsar is? Okay. So a pulsar is a type of neutron star. This is very cool. Now everybody perked up. Everybody woke up a little bit, maybe. A pulsar is a type of neutron star. So a pulsar, or really a phase in neutron star. Pulsar is a type or phase in a neutron star's life. Is a type of neutron star. Okay. Okay, well then that raises the question, well, what the hell is a neutron star? So, well, as you probably know, stars of different sizes stars undergo different life cycles. And the ultimate fate of stars will depend upon really depend on their initial mass. So a star the size of the sun will ultimately end up collapsing to a white dwarf when its life ends. A star of larger mass will collapse into something called a neutron star, and the heaviest stars will collapse into something that's called a black hole. And when I say collapse, what I mean by collapse is this. Well, ultimately, a star lives its entire life in the state of dynamic equilibrium. Hey, dynamics. There are two forces acting on a sun throughout its entire life. So you have your star here, probably a lot rounder than that, generally. And there are two forces. The first one, the inward force, is of course gravity. A star, in case you didn't know, stars are heavy. They weigh a lot, they have a lot of mass, and you have a lot of mass next to each other. You're talking about an enormous amount of gravitational binding energy holding these things together and wanting to pull these things together. So gravity wants to pull everything inward to a point of zero density. So what keeps a star from collapsing? Any idea? Huh? No, it's not magic. No, it's nuclear fusion. Atomic fusion. The enormous energy of nuclear fusion. Look up in the sky and you see a never-ending thermonuclear explosion. A never-ending hydrogen bomb going off, many, many thousands of times the combined nuclear arsenal of the entire world's nations and armies going off every second. Probably millions of times that much energy, released every second, and the whole thing is kept together by its own immense gravity. So basically look up in the sky and you're seeing an enormous nuclear firestorm above you, and that is what we're orbiting around continuously from the moment we're born to the moment we die. It's the moment we die. Isn't that lovely to think about? And so you have these two forces that are these two enormous, colossal forces that are balancing out, and the way they stay in equilibrium, like I said, it's a dynamic equilibrium. And at first you might think, how in the world could such a thing remain stable? You're talking about, this giant nuclear explosion. How could this remain stable? Well, the reason such a thing can remain stable for billions of years is because this is self-regulating. It is a self-regulating nuclear reactor. Because the rate of this nuclear fusion is directly related to the density at the core of the star. So, in other words, you have these two opposing forces, and if gravity starts to win, in other words, the star starts to get a little more dense, starts to contract a little bit and pull toward the center. Well, if that happens, then the rate of nuclear fusion increases, and it generates more repulsive force, and that forces the star out further. If nuclear fusion starts to win for whatever reason, then the star will get the diameter of the star would increase, and then that would make the pressure inside, or the density inside, decrease, and thus decrease the rate of nuclear fusion, and equilibrium would be maintained. So this is why a star is stable. So if you could increase the gravity by, say, I don't know, throwing the Earth into the sun if you wanted to. I don't know how you would want to, but say for science, you want to throw the Earth into the sun for science, see what happens, and that would increase the gravity component a little bit, but the rate of nuclear fusion would just ever so slightly increase, and that would balance out. If instead you somehow remove some material from the sun somehow, I don't know how you would do that, it'd be kind of tricky, but let's say you'd tear away a chunk of the sun, well then the gravity would decrease for a little bit, and the sun would simply expand, puff out a little bit, and then the rate of nuclear fusion would decrease, and everything would remain in equilibrium. But anyway, this cannot be maintained forever. Why? Magic. Oh my god. No, it's not. It doesn't have anything to do with half-lives. This is not radioactive decay. We're not talking about. We are not talking about, say, uranium decaying into lighter elements. We are talking about the much more fundamental reaction that would be something like hydrogen plus hydrogen goes to helium. We're talking about much more energetic reactions. We have not learned how to master this on Earth yet to generate electricity, but if we could, it would completely transform the state of the human species at a fundamental level, because the amount of energy that we could release. I mean, hydrogen is the most abundant element in the universe. It literally is. There's an entire gas giant of the stuff floating out as Jupiter. I mean, we could just pull hydrogen off that from now until the end of time, and we have no problem finding all the energy we could ever need. Or even in our own oceans, there's so much hydrogen that we could power all of our civilizations, even a civilization 100 times the energy we need from now until the end of time with no difficulty whatsoever. There's so much energy potential in nuclear fusion. We could just burn the oceans essentially, and we'd never miss the water that's in there. So anyway, but sorry, I'm getting excited now. But anyway, so this is what's powering the stars. This is what's powering all of the stars when you look up in the sky. This is really the most fundamental reaction in the universe. It's what powers everything else. It is nuclear fusion. But so this is what's powering everything. Well, this can't last forever. Stars live for a very long time, but they do not live forever. Eventually, the hydrogen runs out. It runs out. It is born. A star is born with a certain amount of fuel, and when it's done, it's done. And it's not directly like a gas tank. It doesn't. It's not that it reaches a level where it's completely empty. It's more like It's more like a thing where there is a critical concentration in the core that beyond that, if it's half waste products, then it can't maintain fusion anymore. And I'm going to gloss over some of the details about intermediate stages and things like that. But the general rule is that it runs out of fuel. It's running out of gas. It runs out of primordial hydrogen. It cannot create helium anymore. This is the thing that really generates energy. And once that's done, it's over. And so it goes through a stage known as the red giant phase, but we don't need to worry too much about that. What does matter is that once this outward force is gone, it's going to collapse. And it's going to collapse into really three possible things. It can collapse into one of three things. A white dwarf, which is for stars about the size of the sun, which is approximately, it's about the mass of the sun. It's held up by electron pressure, the kinds of things that would really hold normal matter together. It's still mostly normal matter. It's electron degeneracy pressure. It holds these things up. I'm probably misspelling generacy. Basically, electrons don't like being forced. It's just electron clouds not wanting to be forced too close together. And this is about the mass of the sun and approximately the diameter of the Earth. So it collapses to an object of enormous density. And this is for objects approximately for stars approximately the mass of the sun. They'll end up something like this. For larger than the sun, I forget what the exact limit is, but for larger stars, will collapse into a neutron star. This is where electrons, in other words, even electron clouds can no longer hold matter apart. Like when I say electron pressure, what I mean is imagine pressing your hands together with enormous force. Well, matter doesn't just like sliding past each other, right? That is electron clouds resisting being crushed into other electron clouds, right? That is electron degeneracy pressure. You can only squeeze an electron cloud so close to another one, and that the theoretical limit of that is called electron degeneracy pressure. Now, past a certain mass point, though, if you could squeeze your hands together with enough force, they would slide right through each other. In other words, if you could somehow overcome that electron degeneracy pressure and overcome the force of electron clouds and push things down to nuclear densities, the densities of the atomic nucleus, that is what the kind of crazy object you would get with a neutron star. It is held up, it's basically held up by neutron degeneracy pressure. So, at enormous forces, we have neutron pressure. So you're applying an enormous force, and these things have approximately the density of an atomic nucleus. Imagine taking the entire density, the entire matter of a star, and compressing it under hellish gravity to the point where it has the density of an atomic nucleus. And if you remember your chemistry, you'll remember that the atomic nucleus has immense mass densities. Imagine an entire star compressed to that kind of densities. So this is neutron pressure, and you have the mass of the sun, or approximately the mass of the sun, and approximately 10 miles across, or a few miles across. The size of a city. And I just wanted to introduce these, and then I will discuss what a pulsar is. And so we have the mass of the sun compressed to something a few miles across. Can you imagine what kind of enormous, hellish, incredible forces are there? The magnetic fields of these things are so strong that they would stretch individual atoms into ellipsoid shapes. Imagine stretching an atom into a tube. Think about that. Imagine stretching a single atom that wants to be a sphere, and under the incredible magnetic fields of these things, you're stretching them into a tube. These things have such incredible gravity that if you were to drop an object from, say, the height of 1 meter, literally from the height of 1 meter above it, and release it, it would have approximately the velocity of maybe a third of the speed of light by the time it hit the ground. Think about that. Think about that, how incredible that gravity has to be. These things have such incredible gravity that they significantly distort the light around them. So when you're looking at them, you can see more than 50% of their surface area because some of the light from their backside is being bent and reflected around them. They are distorting the space-time around them. These things are incredible. The only thing that is more incredible than neutron stars is what happens if we add a little more mass. What do you think happens? What's the next stage? The final stage? A pulsar is a type of neutron star. Well, I'm sure you've heard of this. This is a black hole. So the neutron star is the final tormented hellish state of matter, we've taken normal matter, normal plasma, and put of the sun, and compressed it into just a big pile of matter held up just by electron pressure. Then if we apply, so this is normal matter. Then we've added more and more mass until normal matter gives up, and we have atomic matter, the density of an atomic nucleus, held up by, so we have this insane object held up by neutron pressure, and we keep adding mass until finally matter gives up entirely. Gravity wins. Matter gives up entirely, and we're not left with nothing more than gravity. And really, if someone asks me what a black hole is made of, I'm going to say a black hole is just made of gravity. In other words, if you want to think of this, it's almost where the matter ceases to exist at all. You can consider it a pile of matter compressed to an infinite density, but I consider it more that, well, energy and matter are really equivalent. We know this, right? We know that matter and energy both generate gravity. So if you had a big battery and charged it up a bit, a bunch, it would actually have a slightly higher gravitational force after it's charged than before. Energy is matter, matter is energy. They both generate gravity. So the weird thing about gravity is that gravitational fields themselves generate gravity to a certain extent. So gravitational energy does generate gravity on its own. So the way I conceptualize black holes is that they are just piles of gravity. So the matter has completely ceased to exist. We have only a region of hellish gravity, and space and time are so completely distorted within them that there is literally no way out of them. So anyway, I like talking about this kind of stuff. It's kind of cool. This is matter compressed to the point of non-existence. To the point of non-existence. And we can define the radius of a black hole in terms of the radius of which nothing can escape, but I just think of it as matter compressed to the point of non-existence, or infinite density. This is where matter gives up. It doesn't matter. Ugh. Well, if it's flying at you, you'll definitely think it matters. Or infinite. Or let me just say, rho equals infinity. Density is infinity. But anyway, why did I want to talk about this? Well, the thing that brought me on this crazy aside was pulsars. Pulsars are a type of neutron star. I had to discuss a bit about stars before I could describe my example of pulsars, a type of neutron star. So we already established that neutron stars have these crazy magnetic fields, and because of that, they have these crazy magnetic fields, and they often have, and in the case of objects with kind of crazy magnetic fields, if they get particles falling into them or orbiting around them, charged particles, they can get jets. Big jets of particle beams coming off their magnetic poles. So this is the magnetic field, your magnetic field B, basically, if you remember from physics class. And then you end up with streams of supercharged particles, big jets of particles, being injected along the central axis here. Okay, big jets of particles coming from their central axis. Now, the interesting thing about this is that their magnetic axis, their magnetic pole axis, does not necessarily line up with their rotational axis. So they might be rotating like this, but then they have this big particle beam, like a giant space laser, going out from their poles. This is their sort of magnetic beam, magnetic particle beam, being ejected via the magnetic field here. But what happens if this thing is rotating? Well, if you are, because this is basically a giant, think of a flashlight. Imagine if you spin a flashlight around. What happens and you're seeing this from far away, what do you see? Look, imagine a spinning flashlight and you're far away from it. What do you see? You see a flashing light. Light will go on and off, on and off, on and off, on and off. From Earth, or from any distant point, from Earth, the beam appears as a flashing light. And that's why we call them pulsars. Because their light, there's always some light, because the star itself does release some light, but the bulk of the light that we see is this pulsation, so it's just on and off, on and off, on and off, on and off, as a flashing light. And these things can rotate at incredible rates. Why? A flashing light. Let me talk about why they rotate. Well, as we established, or as I mentioned, these things start out rotating, or start out as very large objects. Imagine something, the diameter of a star, the sun, hundreds of thousands of miles in diameter or something, and then you compress it to a dot. So initially this thing might be rotating, I don't know, once every, how fast does the sun rotate? It's many hours, right? Many hours. A period measured in some number of hours, right? Many hours, maybe even days, hours or days, depending on the star. Or days. The rotational periods of stars is in hours or days. And then so this has, even though it's not going very fast, this star has an enormous amount of angular momentum. So it has an enormous amount of angular momentum. But then, this is sort of the ultimate figure skater pulling their arms in. This is the ultimate example of that. So you take this entire star and you compress it down to a point only a few miles across, and suddenly the period of rotation can become milliseconds. So imagine this. We have this hellish star, this incredible amount of matter compressed to an enormous density. Oh, and the whole damn thing is rotating in a millisecond. Think about that. This thing is so crazy, it exhibits a phenomenon in relativity known as frame dragging, where it's actually dragging the space-time around it and twisting it up like a twisted thing. Anyway, it's twisting it like a thread on a spool. It's crazy. So yes, pulsars are absolutely insane, and neutron stars in general, which is kind of why I get so excited talking about them. But anyway, that's the general idea. So again, that is the general idea, but in summation, if no external forces are applied to an object, if no external forces with a moment arm are applied to an object, then the angular momentum of the object will be constant. Even if the moment of inertia changes. The I changes. Let's see what else. Okay? Or also, so that makes sense. All right. And that's the general idea. So, if an external force is applied through the center of gravity, well, then we'll get something like this. We'll have that L1 is unequal to L2. However, HO1 is equal to HO2. In other words, the MV1 is unequal to MV2, but I omega 1 is equal to I omega 2. So this would be an example of this would be something like the gravity of the sun acting on the Earth. It does change the velocity of the Earth in terms of at least its direction, slightly its magnitude as well. But because that gravity, well, is literally applied through the center of gravity of the Earth, it doesn't generate any tendency for this. It doesn't generate any torque on the Earth. It only generates a tendency to translate. So the gravity of the sun acting on the Earth will change its velocity, but it won't change. It'll change the linear velocity and its linear momentum, but it won't change its angular velocity or angular momentum. All right, I think that'll finish it for today. Next time we'll come back and we'll look at some numerical examples of applying momentum, both angular and translational principles to systems of rigid bodies. That'll do it, and as always, thank you.